Good afternoon, fellow engineering colleagues. My name is Roberto Science, and I will be going over my third exam in my System Dynamics and Control class. The problem we were given is this 5y dot plus e to the naught y double dot plus cosine 0 y triple dot plus y sine of 0 equals u. And our assumptions are all initial conditions are at equilibrium. The system is frictionless and it will use ideal spring and dampeners. Right away, we can drop the y times sine of 0 term because sine of 0 is 0. E of 0 turns into 1 and cosine of 0 turns into 1. So this leaves us with the equation we will be working with: y triple dot plus y double dot plus 5y equals u. From this equation, we get the transfer function by taking the Laplace transform of this y triple dot function. And from this, we get our transfer function y of s over u of s, which is equal to 1 over s times s squared plus s plus 5. As you can see to the right, this almost mirrors the ideal mass spring dampener transfer function. Therefore, we pulled the values m equals 1, b equals 1, and k equals 5. From our transfer function, we set it equal to the resonance so that we can find our critical DC gain, the natural frequency, as well as the zeta, just because we have the information. So our critical gain is equal to 1 over k. So that just comes out to 1 over 5, which is 0.2. Our zeta is equal to b over 2 times the square root of km. This comes out to equal 0.224 for zeta, and our natural frequency is the square root of k over m. This gives us a natural frequency of 2.236. With our transfer function, we can also find the steady state final and initial volumes. The final value theorem, we take the limit of s, y of s, and take it as s goes to 0. So the limit of s over s times s squared plus s plus 5 gives us the limit of 1 over 5, which is 0.2. So as y goes to infinity, our final value will be 0.2. Slightly different on the initial value. Instead of s going to 0, it goes to infinity for our y of 0 just right of the 0 number. So plugging in the same equation, we get the limit of the top s and the bottom s on the outside cancel out, which leaves us with 1 over s squared, so 1 over infinity, which equals to 0. So our initial value just right of the 0 will be 0, and our final value is 0.2. Here we have the step response. From the graph, we have a maximum overshoot of 48.5%. We have a rise time of 0.553 seconds and a settling time of 7.56 seconds. We can also calculate these, get a general answer by hand. The settling time is about equal to 4 over zeta times the natural frequency, which yields us about 7.986 seconds. And our rise time can be approximated as 1.8 over the natural frequency, which gives us about a rise time of 0.805, as well as the maximum overshoot can be calculated using the e to the negative zeta over pi over the square root of 1 minus zeta squared. And this gives us a maximum overshoot of 0.486 or 48.6%. Here we have the Bode plot. As you can see, our peak gain will be around negative 6.77 decibels. Here we implemented a negative feedback loop. As you can see in figure 1, we have the general form. C of s is equal to kg of s times h of s over 1 plus kg of s times h of s. As stated before, our g of s is going to be 1 over s cubed plus s squared plus 5s. and our h of s is a unity function, so it's just going to equal 1. Plugging in our g of s, h of s, we get k over s cubed plus s squared plus 5s all over 1 plus k over s cubed plus s squared plus 5s. And then after some simple algebra, we are left with a controller negative feedback loop. C of s is equal to k over s cubed plus s squared plus 5s plus k. Now that we then plot this into our root locus, and from our root locus, we can see that we have 2 poles. One of them is at -5 plus 2.24 imaginary, and the other pole is at -0.5 minus 2.18 imaginary. As you can see, the dampening of each of the poles are reciprocals of each other. So we have 2 poles since it's a 3rd order system, but it behaves like a 2nd order system. And we have no zeros because there weren't any s's in the numerator to give us any zeros. Next, we move on to the root stability criterion using the same closed feedback loop as figure 1. The root stability criterion is ideal for this because it is set up already with the parameters of a 25% maximum overshoot and an error, a steady state error of 2%. So the equation for root stability criterion is f of s equals 1 plus kg of s times h of s, which is equal to 0. Substituting that into our equation, we end up getting f of s is equal to s cubed plus s squared plus 5s plus k equals 0. The general equation for Routh's criterion is going to be all our coefficients on the, starting with the highest power will be a naught, the following one will be a1, a2, a3. So our a's coincide with the coefficients that match up with the s's in powers from greatest to least. So here we have our table. As stated before, this is our function, f of s. And here's the general equation. So we pick it out, we have our a naught equals 1, a of 1 equals 1, a of 2 equals 5, and a3 is equal to k. Here in this middle table, we have the general format for finding the, for using root stability criterion. And basically we have to find the values to plug it into this chart. So we know a of 0, we know a0 through a3, but we still need to find b1, b2, c1, and c2. Those can be calculated using the original a value coefficients and basically just substituting them in. So going back, we end up with a1 is equal to 1, a2 is equal to 5. I'm sorry, a0 is equal to 1, a1 is equal to 1, a2 is equal to 5, and a3 is equal to k. b1 from the previous equation comes out to 5 minus k, and then b2, c1, and c2 all end up zeros because we do not have values following a3. So a4, a5, a6, those are all going to be zeros since we don't have any. Solving for k in the b1, we can find a suitable gain range that will keep the system stable. In order to keep the system stable with root stability, the value of k has to be greater than 0, and there can be no sign change in the second column. So in order for us to not have a sign change in the second column, our k value needs to be lower than 5. Because if it's greater than 5, we will end up with a negative value, making our system unstable. And so our range for k will be 0 to 5, and our critical gain is going to be 5, since that's the one where it changes. We can find our critical period by doing a step response. And the critical period is found by subtracting the times of peaks from basically subtracting 2 times of peaks. So on the right hand, we have a peak at 16 seconds, and on the left side, we have a peak at 13.1. So 16 minus 13.1 is a critical period of 2.9 seconds. Using our critical period and our critical gain, we can then use Ziegler-Nichols method to design a controller for the system to help it behave the way that we want it to. So here we have the general format. This is how you find for each of the different controllers. This is the general format that will go in depth as we design the controllers. So for a P controller using Ziegler-Nichols method, we only need to find the gain, the proportional gain. And to find this is going to be our critical gain over 2. This ends up giving us a proportional gain of 2.5 decibels. For the PI controller on Ziegler-Nichols, we also have to, not only do we solve for the K proportional, but we also have to sign for the integral gain, or KI. The proportional gain is solved by the critical gain over 2.2, which gives us a, with the PI controller, a proportional gain of 2.273 decibels. And then the integral gain is solved by Kp over T of the integral time, Ti. That'll give us, so we plug in the previous 2.273 decibels, and then to find the integral time, you can go back to the chart, and it's basic, and it will be the critical period over this 1.2. So this ends up giving us a integral gain of 0.941 decibels. Lastly, we have our PID controller. This is just like the PI controller, this implements a derivative gain. So so not only do we solve for Kp, Ki, but we also have to solve for Kd, the derivative gain. Kp is solved similarly to the other ones. It's just the critical gain over a coefficient. This one's, or I'm sorry, over a value. This one's going to be 1.7. This gives, so our critical gain 5 over 1.7 leaves us a value of 1.941 decibels. Our integral gain is going to be the same as the last time, Kp over Ti. Using the same method as before, this gives us an integral gain of 2.028 decibels. And then lastly, we have our derivative gain. This is going to be summed by the time derivative times Kp. So this leaves us with 2.9 times 5 over 8, which leaves us a critical gain, a derivative gain of 1.813 decibels. Thank you so much for your time, and I hope you enjoy the presentation.